It's my first time at CppCon. I've thought about going for a lot of years and now kind of regretting that I didn't go sooner.
Okay, welcome to High Performance Cross-Platform Architecture. I'm Noah Stein. Just to check, this is my first time presenting at CppCon. Is this readable? Yep. Good, because I hate talking about myself, so you already know I don't have to. But I will mention out there that the first cross-platform project I ever worked on was back in 1994. I was lead programmer of a game that was on the original PlayStation, the Saturn, and PC, the old DOS. And they were three completely different platforms, different CPUs, different graphics systems, I/O, everything. From that time, I've just continued to study that, study cross-platform issues, and recently I looked at, does C++20 offer us anything that can take this to another level? And I believe so. Now the goals of this cross-platform architecture are to take advantage of all the platforms, to be optimized on them, to be able to use their different features. The solution focuses on the compiler. I want that's what the standard really covers, and I want to minimize what happens in the build. And actually there's only one preprocessor macro that gets set in order to use all this stuff. So moving between build systems should be easy. I want to minimize boilerplate and unnecessary code, minimize redundant code. If you wrote something and it should work, then it will work in other situations. I want to minimize modifying existing code when I add something new, whether it's a new platform or a new revision of a platform. And I want to minimize use of preprocessor macros. There's not a single if-def in what I wrote to support different SIMD architectures on different chips. So here I'm going to walk through designing a Quaternion class. Not all of you will be familiar with it. It's used a lot in 3D graphics, some physics, some physical simulations of astrodynamics. We're going to walk through the project build issues, a systematic method to include the header files, which is one of the keys to making this happen. The concept hierarchies and the class and function design that just bring it all together. There's a fundamental overriding principle that drove the development of this, and that's the open-close principle. In C++, it was first brought in 1996 by Robert Martin, C. Martin, in an issue of C++ report, long since gone. Open-close principle, it means that it's open for extension and closed for modification. As presented to the C++ community, the example was implemented via delegated polymorphism. In classic C, what we saw was that if we wanted to draw a bunch of shapes, a collection of shapes, we'd create an enum that told us what the shape was. We would put it at the start of different structs, such as a circle and a square. We then had drawing functions for each of those types, the circle and the square. And then the draw shapes routine would just iterate through and switch on the type, and then in these cases, it would cast to the appropriate struct and then call the draw. Now the issue on open close there is that whenever we add a new shape, such as an ellipse, we're going to add a new case to that draw. Now that the draw shapes is the interface. So the code that's directly being seen is being modified, and that's a danger to clients that those changes could cause breaks, could break the clients. The C++ solution, the object-oriented solution presented by Robert C. Martin, involved having a base class of shape, having a virtual draw call, then the circle, the square, and the other shapes would derive from the base shape. Then the draw simplifies out to just a simple iteration. You get a pointer to the base class, and then you draw. The draw is automatic through the virtual. You get the correct drawing call. So when you add a new shape, such as an ellipse again, you end up creating a new class. Nothing changed in the call to draw, and actually nothing changed for circle or shape even. So you were extending it without actually modifying the interface. Thus, you have a lot more security in knowing that you're not breaking things. In researching this talk, I found out that the earlier version has a slightly different, let me pause. Bertrand Meyer in 1988 actually defined the open-close principle, 8 years before Robert C. Martin brought C++. His definition is a little bit different. His definition is that once you have released code into the wild, you want it closed. You don't want it modified because clients rely upon it. And as I already said, if you change something, you can break something else. But you want it open for extension. What's interesting, though, is his example is very different than the one we know in C++. He uses direct inheritance. So you don't see, I've never seen that in C++. You would have everything virtual in your class. Then you would, if you wanted to make a change, you would subclass it, change the virtual functions, add whatever, and get your new thing. But that means everything in your program would have to be by reference, by pointer, not by value. I would show an example of that in code, but I can't think of one. So what I did do is reproduce faithfully, visually, the example from his book, Object-Oriented Software Construction. So if you have a class A, if B, C, and D are clients of it, depend on it, and then E depends on C, when you want to extend it in the open way, you actually subclass off of A. And then anything new you write will interact with this A prime. All the originals will still work off of the older A. So B, C, and D will still work off of A. And I've just never seen anybody implement anything that way, oddly enough, until now. I didn't realize that I followed his original design methodology on the open-close principle. So I like to, I think there are two flavors of the open-close principle when we get in C++, it being a compiled language and with the way it's structured. So first let me start with, there's no consideration for the open-close principle. If you're going to go back and you're going to modify previous code that you've written in order to add a new feature, that can potentially change the current behavior or the interface. And that means that your clients that use it are going to have to change in response, and their clients might have to, and it's just going to all ripple out, and it's going to be a lot of work and potentially bugs and a lot of time. Now, when we get to actual OCP, I like to think in C++ that there's two flavors, a weak and a strong. In the case of weak OCP, you are modifying previous code, but there's no visible change to clients in the current behavior and interface. And therefore, what you will see is a recompilation, but you won't have breakage and you won't have other problems associated with it. A perfect example would be if that draw was in a larger class, say a renderer, and it had other functions unrelated to drawing. If you added something there, that would be a weak OCP extension, if it doesn't affect the draw. In the case of strong OCP, when you add a feature, you in no way modify any pre-existing code. And what you'll see is if nothing uses the new feature, nothing recompiles in your build. And we'll actually see this later on. So my design here is not OOP. I have separate data and separate functions. They're free functions, not member functions. However, depending on what you're doing, it does work with OOP. That's not strictly a limiting feature, a limiting factor. Whenever I add a new platform, no previous platform changes. And that can be seen in that when I make changes on one platform, I can push the code up, other people can pull it down, and when they rebuild a different platform, nothing compiles, nothing rebuilds. These are isolated platforms. The code is totally isolated from each other. At the same time, when I add a new revision, such as going from SSE to SSE2, it's the same rule. If I had a project that was still on SSE, the original SSE, not SSE2, it will not recompile. No prior code is modified in order to take advantage of some new feature. So then the question is, what is a platform? Simply, it's a specific set of features. Thus, the next question, what is a feature? Feature is an abstract unit of functionality requiring a separate implementation depending on the machine's architecture. Some features are hardware. You have the CPU architecture, SIMD instruction set, DMA controller, other aspects. And then there's software, such as what operating system you're on, the graphics API, et cetera. And those features may not be totally orthogonal. You don't have SSE on ARM ever. You don't have Neon on the Intel chips. However, you do want to treat them, SIMD as a separate feature from any other CPU-related feature because those things can revision at different times and in different ways. And one day you might find out that they did change in different ways and your assumption broke it. I ran into that one time where I was brought in on a contract on an embedded project, and it was a new chip from the manufacturer they buy from, and I was working on a new platform, taking the old software and moving it over. Unfortunately, all their prior chips had newer and newer versions of ARM cores. This one had the same one as a prior chip, but it had a different DMA controller. All the other things were different, and the problem was then when I had to go back through all this code and figure out, checking for that ARM version. Is it really about that ARM version, or is it about the other hardware? And it was a nightmare. I highly recommend define separate features separately, even if they're related. Next thing to get into is directory and file structure. The inclusion methodology used here is heavily reliant that you structure where you place your header files. Now, that doesn't mean there's only one way to do it. And what I wrote this time, I have everything flat. So in this case, I have a SIMD section because SIMD is my feature, and I'm going to define some tags related to that. In my math section, where I'm actually going to use this feature or define things based off that feature, I put things flat also as the example there. But in the past, I've actually done them deep, as in the other example on the right, where all my Neon 32 stuff ends up in its own directory. What you do is up to you. It all depends. You might have more files than you want, less files. It might be more complex. There are reasons either way. It's your decision. There's always, it's software engineering. It's figuring out which decision to make, which way. So when you include a header, each feature gets its own header file. So in the case of SIMD, there's going to be a simd.h. And this header file is generic to all of the platforms. But what it's going to do is it's going to use these preprocessor macros. As an example, include SIMD quat. That's going to turn into a string, quat_sse2.h. And that is going to be at the bottom of my quat.h file. And that allows me to then pull in, if on SSE2, that's on a machine that I've said is going to be SSE2 based, that's going to pull in SSE2. Obviously, it'll change the other names, but that's a key element in avoiding including other platforms in there. Not using an if-def to say, well, if I'm if I'm SSE or I'm Neon, and then pulling in one or the other. This way, I never see the other files. Only the one that's related to what I'm doing. So the header inclusion macros, there's only a handful that I have now, and I have include PLT for including a platform. That then delegates down to include build file name. And build file name is the most difficult of the group, the most complex of the group there, because it just, it pastes the tokens together with the double hashes and the underscore, and that's where you get the quad_SSE. That actually has to dump off to the include string eyes. When you paste tokens together in the preprocessor, it actually does not do macro substitution. So you have to push it once more to the bottom one to get the macro substitution to occur, and the hash puts the quotes around it. So what I end up with at the bottom of my header file, my one header file for SIMD in that case, is pound include, and then the macro include PLT. I then define, we'll get to it again, but I then define include SIMD in the SIMD file, and that is to ease everything I do that's SIMD related versus, say, graphics or whatever. The top macros that are separated away are all in PLT.h. So they're common to everything. Once I have SIMD, I define include SIMD just as a way of more efficiently using it in everything it uses that relies upon SIMD. So now we want to create a feature. Now that we know how to include files and these header files and how to structure them for the features, so we need to define something in the build system. That's the preprocessor macro I referred to before. Create the header file, as I mentioned, and create one header file for each unique implementation that I'm going to make. So back to the example of SSE, if I want to support SSE 1 through 4, I'm going to have an SSE1.h, SSE2.h. So in the build system, I'm giving some examples in CMake. I basically have 2 lines to support it. I set a variable in a toolchain file. So each platform has its own toolchain file. Then in the common project, I'm going to add that definition in. Now, the other thing that you probably have to do is set your compiler to say which architecture you're going to use. Everybody uses whatever compiler. There are different ones. I'm not going to say I do that. But those are the only 2 things that need to happen. But you already had this. I'm just saying I only added one more step on there, creating this preprocessor macro. But when you set it, you're also going to set your compiler flag. In the case of the feature header, this is the one place where I do have a pound if. It's not mandatory, but what it does do is just make sure that they set, in this case, PLT SIMD. It's a sanity check. It's not strictly necessary, but I advise doing it, but it's the only if you'll see in the code other than the include guards. As I mentioned before, pound defined include SIMD, and the pound include PLT local, PLT SIMD, that will now include the specific feature header. So, for example, SSE2.h. And if you don't have a specific one, I use the word common to define what's going to be a common implementation to all versions. So the first thing it would load is common. Since when I'm developing, I haven't written anything for any specific platform, and I write a common version first that will compile everywhere that's not optimized other than what the compiler can do. So all I have in that SIMD.h, other than some include guards, et cetera, is I define the struct common, which is my tag type. Let's move over to Quaternion, a short discussion of Quaternions in order to talk about what's going to come up next. Simply, it's a 4-dimensional complex number, has a scalar and 3 imaginary components. There are some relationships in there that affect the definitions. Addition is straightforward component-wise. Given the definitions of the 3 complex components, you end up with multiplication that is that giant mess at the bottom. It has some functions on it in addition to those, such as conjugate. The specifics aren't that important. It's got a dot product. There are other things we could say mathematically about it, but it's not really relevant to this discussion. Okay, so mathematically, the definition of a quaternion is its data and its operations. As far as a C++20 concept goes, it is only the structure of the data that matters in this case. The common implementations we write will work off of that concept, and then later on, we will specialize and create the optimized versions of these functions. So what does the concept look like of a quaternion? Here it is right here. I'm not going to do a full tutorial on concept. It's somewhat self-explanatory in parts. So a concept is a template. In this case, we only care about one class, quaternion Q. The requires clause is going to be used to place some requirements on the type that we use for a quaternion. In this case, it has to have a type name defined in it, scalar. Arithmetic we'll get to in a second. It just says that the type has to have arithmetic functions. Now the 4 on the bottom are 4 accessor functions for the W, X, Y, and Z. In this case, what that text down there does is it says that a call to Q.W must return a type that is the same as the scalar type. This is the only requirement on the class that represents any quaternion class that you have. So in this case, the arithmetic's really easy. I use the standard is arithmetic V type. It's going to come up in a couple spots. I created a mutually arithmetic concept. And in this case, it requires that both types be arithmetic, and then in this case, that they have to have the mathematical operations together of addition, subtraction, multiplication, division. Any type that meets this requirement will work. Any built-in type, it could be any custom type then if you have a fixed point type that you've created. So now I'm going to define my standard quaternion. You can have any quaternion type you want to create can work. In general, you're going to work with something dense. So if we look at the declaration of this standard quaternion type that we're going to use, it has a template. The type name S is going to be the scalar type. Which is I use short for instruction set architecture, is going to be defaulted. As you see, it says PLT SIMD and then PLT underscore SIMD. So it's actually going to have a default value that's sucked in from that preprocessor. And that's where some of the magic comes in. Because again, once we defined SSE as our platform SIMD, now we have a request here for what we want as our ISA. So it defines the scalar that we said. There's 4 data members, which are part of the mathematical definition. It's going to require a few constructors. It's going to have a default constructor, which will be default of a constructor which is based off of its 4 components. I put in a move constructor. Now in the case of floats, most types you use, you probably won't need it. That's there because if you had, say, a big number type, you could end up with moves, and therefore you would need that. Most of the time you don't, and if your use cases don't require big numbers or something else like that, don't do it. Now there is the concept constructor. And in that case, we're checking to see, the requires statement there puts a constraint that the scalar of the source quaternion must be convertible to what we're storing. Then it's just, at that point, it's very similar to the component constructor. So these constructors you'll see in every type at some point. There's an assignment operator. It's actually just, it's the concept constructor as an assignment, essentially. Then we have the 4 accessors. In this case, they're really simple, straightforward. Now, the operations for the common are implemented as an expression tree. And they're designed so that they can run anywhere. Works for any arithmetic scalar type. So again, if you create a type in the future, the code that's going to come out of this general implementation will work. So here's an example of an expression tree is if the compiler sees Q1 plus Q2 plus times Q3, it's going to end up, as the operators come in, they're going to create structures that have references to the quaternions or to other operations. So here's an example of the addition operator. It's going to take the 2 sides, which could be anything. They could be trees themselves, expression trees, and they're going to create an addition structure. Now that addition right here, that is going to happen to have a type name. It's going to define scalar, and eventually we're going to define, we're going to define the accessors, which are just the addition of the component-wise elements, just like the mathematical definition. And at that point, we have addition in the expression template tree. And when we do an assignment from that concept constructor, we have addition working. Now, we can implement then subtraction, other elements like that. Here's an example of a scalar value function where we're starting with a quaternion, but we're ending up with a scalar. That one's much easier because it's just a straight function. And here we evaluate the expression trees because the left side and the right side are just any kind of quaternion, and an expression tree that's quaternion valued is a quaternion. Once we use this, that's just a regular function. There's nothing special there. once you've defined these things, all the client code is just normal code. Now we've completed the common implementation. It'll compile and run anywhere. It's only as optimal as the compiler's optimizer can make it. Now let's do the ARM Neon first, because let's say we're most interested in a mobile thing. We're gonna come in and we're gonna update the build system, set it to Neon 32, the Plat SIMD. In this case, it might be a separate tool chain because we're adding something. This might be our primary, so we're changing the current one. So the Neon 32 feature header, we include SIMD.h, and then we create a Neon 32 struct that derives from common, and create a concept. That concept then, Neon 32 family, is gonna check to see is a class derived from Neon 32. And that's very important when we get to overloading. Class declaration, well, instead of 4 floats now, we have a float 32 by 4 value, which is what's defined in the inline ARM Neon spec. We define our scalar. Constructors, very similar to the other constructors, the only difference is we have to put it into the ARM Neon format. The accessors, they're 4 very simple accessors, but we need something specific to what the Neon 32 is. There is one additional accessor, and that's to the raw data, this Neon val at the bottom. Unfortunately, that is public, and that means if someone could potentially use it, that's the one Achilles heel to look at, and I don't expect it to be used all that much outside of that platform-specific code, but it is there. So where are we now? Just by defining this alone, we can compile now. Even though we set the macro, we're using that Neon 32 specific type now, and it's actually being used. We don't have optimized functions, but when we pass it now, it'll pass through a Neon 32 register. Everything runs because we had those expression templates. Because this is a valid quaternion, because it has its accessors and all of its glory. But now we can write an optimized function. So in this case, we have a subtraction, and wow, is that really what I put there? So in this case now, we've optimized the operator minus, oh no, I'm sorry, that's a negation. What am I saying? So we've optimized this one function. If you look, we have a template. It's a templated function, and it's templated on the SIMD, and it's in the Neon 32 family. So that quaternion that's being passed in there, if you look, it takes a float, and it has to have the Neon 32 SIMD tag, or there's a Neon 64. A Neon 64 would also be passed in here, because in the template, that specification is a constraint. It must match the Neon 32 family construct. So that tag must be Neon. Common will not be matched here. So in this case, now we put this in, again, if we recompile, now we have an optimized negation. And we're getting somewhere. We do that for all the other functions. Now we have a fully optimized quaternion. Whatever code we have that was running on common is now fully optimized for the Neon. At this point, we can push up all our code, somebody else can grab it, and they're working on a PC and they have SSE. They go to recompile their build for the PC. Nothing compiles for them. There are no files changes, nothing rebuilds, nothing links, because none of what we just did for the Neon got included, because the headers were all included through that Neon, through the Neon definition. So now we're going to do the SSE. We're going to add a platform over here. Create the new toolchain file. We define the SSE. No changes required at all to the common part of the build files, nor to any other toolchain file. We'll create an SSE feature header now. It's just like the Neon one, only it says SSE. It has its own concept, its own tag. Again, it looks a lot like the Neon version, except it's an underscore M128, because that's the SSE value used by inline. Because we included imintrin.h, which will never get seen, by the way, over on the Neon. This file never gets loaded on a Neon, on an ARM device. Therefore, there's no if-def anything wrapping the include. We can directly include because we know we're never going to be on that other platform. Accessors, a little more complicated, but that's what SSE gives you. So now we do a dot product using the first version of SSE. There's a few steps there. I'm not going to get into the specifics of SSE optimization or anything like that. This is there for comparison purposes. You know, there's certain limitations. You have to move stuff around. Nonetheless, it's going to be faster than doing it through the common method. So now we have the two platforms. Totally out of order. So now we have the two platforms. Both are optimized, both are running, neither one affects each other. You can make whatever changes you want, the files are separated. But we do have a time to do revisions now. There's SSE 2, 3, 4 that have popped up. Like in the case of SSE 2, doubles were added, so now we can optimize doubles, not just floats. So in the SSE 2 feature, typo. So in the SSE 2 feature, we define that as deriving from SSE, and then we define the concept for the SSE 2 family. Now this is slightly different than the SSE one, because it doesn't just have derived from SSE 2, it also has this SSE, it also checks for the original SSE. And there's a reason for that, and we'll get to that in 1 second. So in the case of the move from SSE to SSE 2, the register format didn't change. And that's reflected in our code by just creating a specialization of quat with the float for the SSE 2 that derives from the original one and just does a using on the constructors. The one thing we have to bring in is constructors. Everything else we inherit just by having the class and the public derivation from it. Whoa, wait a minute, what was that? Okay. So in this case now, we've created the double for SSE 2. It's slightly different because you only get 2 doubles in the register. Other than that, you can see the structure is actually very similar to the other two. Again, the specifics here don't really matter. It's just that we can have more than one data member in there. Put the accessors in. This time we have 2 data accessors because we have 2 different members that have data in it. And again, once we compile with that, we now have doubles sitting in registers being passed around that are quaternions. We do a dot product on there, implement a dot product for it, we implement everything else, then everything's optimized. So you can see the dot product's a little bit different because we're dealing with 2 separate things. It's a little bit longer. SS3 comes out. So it's the same thing. We do the same thing that we just did, but something new is going to pop up in here. And that is, we have new instructions that allow that floating point and that double to be more highly optimized. So we're going to create new functions that are templated again off the SIMD tag type. And this is where, let me go back. This is where it mattered about our concepts. When we derive you can't inherit one concept from another. So what we have to do is, actually, I have that discussion coming up. What we have to do is, for function overloading, we have to rely on something called subsumption. If we merely hold on, okay. Concepts are like enable if, they allow you to constrain the visibility of something. But unlike enable if, they actually play a role in overload resolution. And in normal overload resolution, if one class derives from another, it has a higher priority. It's going to be chosen first. Unfortunately, in concepts, like I said, we don't have derivation like that. But what we do have is subsumption. And what that is if one concept references another concept, it is more specific than that, and like a derived class situation, it will have preference in overloading, in overload resolution. And therefore, that's why the SSE2 family concept makes a reference to SSE1. Because if we look at the strict definition of derived from, they both use derived from, one from common, one from SSE. But by definition, if you derive from SSE, you derive from common. But that's actually, that would be ambiguous in a concept situation. It takes, because both concepts are valid and one does not refer to the other. You need to have you need to have a reference of a derived concept in order to have overload resolution, in order to have a difference, make it unambiguous. Because a concept that subsumes another concept has a higher priority. So the subsumption code, we can see it here. So SSE derives from common, SSE2 from SSE. When we look at the family definitions, when we get down, we have SSE family, which is just derived from SSE. SSE2, again, you can see the SSE family SIMD and the separate derived from, and that creates the ordering right there. If I did it just the second one, as you see SSE2 derived, which is not used in code, that is the one that will cause ambiguity if you just have that derived from, even though, again, it's more specific in some ways. Oh. Okay, this is basically just what I said. I got ahead of myself. I apologize for that. So, what's subsumption? Okay, so with SSE3 now, we now have overloaded functions, and they are being selected properly. And again, if I rebuild for SSE3, I now have the more optimized dot product than I did before. All the other versions were inherited. The addition didn't change, so the addition's still going to be valid. I don't have to retype it or do something or every time, every generation to generation. Everything is valid in the new revision. It's just those things that you overload that change and get used, and it's all clear. It's all clean. But now let's look at AVX though. AVX was a standard after SSE4 where instead of having 128-bit registers, they have 256-bit registers. Now we can actually fit those doubles into one single register. The quat float in this case won't get any additional advantage. There's nothing to do here, but the double now, we end up with a new data type because it fits in a single register. So in the definition here, when we have an AVX quaternion, we have that single now 256-bit version. When we go and compile with that, our compilation will fail, unlike all the other times where it worked. And the problem is that because we inherited from SSE3 or SSE4, we pulled in all those functions for SSE4, but they worked with a different data format. So this will fail to compile with how we've been going so far. This illustrates two issues coming up. One is that we should separate the data from the functions. Those should be in separate header files. And that's actually a good thing because there's a lot of places we'll want to have the data, but we're not going to operate on it. We're going to move it around. We're going to store it. So why throw a dependency against operations that we may add to or change? But there's a second aspect to it, and that is that will still not avoid a compilation error in this case because we were still pulling in, even if we had all the operators in their own file, we are going to be including the prior version's file. That's going to come in. We're still going to have the error. What we really need to do in this case is we need to treat the operations file actually as just a simple thing that it's a method of indirection. We're going to include other header files that for each type. So what we're going to see is like quat operations quat math is going to include AVX, is going to include quat float math AVX, and quat double math AVX. We want a separate one for each specific specialization that we have for each thing we're handling because they're gonna work separately. Now, we can't fully separate them out because all of this falls into a quaternion, and that's our primary interface in these headers. But by having our specializations in separate files, in the case of double, that double math avx.h, that will not include the prior revisions versions. And that means we don't pull in these out-of-date operations that work on the prior data format. Quat float math, on the other hand, will include the previous generation because it is still a stable data format. So how could you know that from day one, that that's the way you should have? You probably couldn't. I didn't. Given how large the code base is, I mean, refactor it when those times come. Now, in this case, getting back to the OCP aspect of it, you are making a change that's causing a recompile, but it is purely a structural change. You're not changing a single line of code and how it compiles, so it is a very safe change to make. Thus, it's officially weak OCP, but it's actually very strong. In summary, we can write optimized code for each platform. We can isolate the platforms from each other so that whenever you write code for one platform, it is never seen by any others. You can be safe knowing that you're not going to break anything by working on one platform instead of the other. We can minimize the redundancy of what we're doing. In no case was a function rewritten that was the same behavior. Functions were only rewritten generation to generation when there was a better function that could be written, better implemented. Otherwise, we were able to get it coming forward. And with C++20 concepts and the discipline of how you include headers and things like that, we can have it all at once. I have an outdated version of this on GitHub. That's the link at the bottom. Some of the names are a little different. It's also in, there are alternate ways to do some of this. I have a version in there where instead of having one single template class tree that I'm specializing in different ways, instead each implementation, the quaternion float for SSE versus the one for SSE5 or Neon, there's no SSE5, or Neon, all of those are completely separate classes, and then they get unified via a using mechanism. That's another way to do it. It has some advantages. It actually has a little bit more boilerplate, so I don't necessarily recommend it. And then there's also some alternate little things here and there that you can do alternate ways that are roughly equivalent. You know, that's user preference. That's an engineering choice. Other than that, I can get into some future directions or possibilities, but that's the general gist of it. Thank you. Any questions?
Great talk, Noah. Thank you so much. So my question was, you had SSE2 derived from SSE, right?
Yes, SSE.
And you mentioned the only thing that you had to do was implement the constructor, assuming there's no change from SSE to SSE2?
No, because, well, that's in the build file you do that.
Okay.
So when I go to, when I have a platform that is SSE2,
yeah,
the way the whole thing knows that it's SSE2 is in your build file, you're going to say that PLT_SIMD, define that as SSE2. Mm-hmm. Now, let's say you were on SSE1 and SSE2 spec just came out.
Yep.
And you're just implementing it. Literally, you just flip that switch. And then you're going to be compiling as SSE2. Mm-hmm. If you want it, I mean, you wouldn't switch from SSE2 to Neon, but you could flip that switch too. I also have it working in Scripting. There is a WebAssembly SIMD spec. So, you know, you can use all kinds of platforms.
Nice. So if nothing changed between, let's say for your implementation of Quaternion, nothing changes from SSE to SSE2, nothing changes at all. Do you still have to implement the constructor for SSE2?
Okay, so you still have to do the, well, strictly speaking, no, you could get away with a using. Mm-hmm. I would recommend against it. You could do a using and it'll pick it up. No, wait a minute, that's actually over on my using side. No, you do have to define it because you do have to define it as a specialization of the template. And in the using side, you don't have to, I still do, if you do it that way, but you do definitely have to do it in there because it needs to kind of slot into the master template there.
Awesome, thanks so much.
Yep.
So I really appreciated the whole idea of build configuration versus conditional compile it. But one of the things that I found in some of the things that I've tried to do is there's a proliferation of all these alternatives, and to tease out the pieces that are dependent on various options, you get this huge tree of files to go, and it's like, well, what am I, if a developer, particularly somebody who's new to the project, what's being included? You know, have you run into that problem, and how do you deal with that?
Well, I mean, I haven't, this is actually playing around with C++. I only have a small prototype and tests written for it. I haven't used it in a large one, although I have done some similar things in the past, actually. I haven't particularly had a problem with it, as long as you know on your platform that, because they're going to be in file names. You're pulling, you don't have multiple platforms in a single file ever. So you're pulling in by separate files, and you're going to, if I'm using quad, I know that I can look and see the other files in the directory with it are quad_SSE, SSE2. So as long as I know what I'm building, which is in my build file, I'll know which files to look at. You know, I would imagine unless you're jumping around between 20 or 30 platforms, you're gonna know what you're on and have a pretty solid focus on what your files are that you're using.
The other question I had was regarding subsumption, which you were talking about. I kind of lost you on a little bit. But I was wondering, had you looked at CTAD deduction guides from C++17? Would that have helped you at all?
I didn't look at that. CTAD. Oh, deduction guides. I don't think in this case the deduction guide is what would work. The tag gets used in that class to choose your specialization. And I don't see how a deduction guide creates a specialization. It does do a transformation of types. If there was something that came in from the outside, it's interesting. I wonder if there's implications for other aspects of it.
Hi, I'm curious, comparing to other like open source available SIMD libraries, which there are like dozens of them, what are the improvements in this library? And did you consider contributing those improvements into some of the existing libraries?
Oh, I would definitely consider contributing it. It could slot in potentially in a number of libraries just because with the concept, like I said, anything that looks like a quaternion, that is which doesn't even enforce a constructor. All it enforces is you have to have that W, X, Y, and Z accessor, and that you define a scalar type. Those will automatically at least run through the common section. So as a first step, create a facade over any other quaternion type, as long as they don't have different data types for their 4 different components. You could write a facade and you'd be able to use it with anything, and then push in then write your different specializations as you move along. But yeah, I think dozens is probably the low end of the number of, of libraries out here that are, I'm an optimized quaternion or whatever. The key here is I can now, with one set of code, be optimized for SSE, for Neon, for AltiVec, even in WebAssembly, because there's a WebAssembly SIMD spec, I can be optimized on there too. It's identical code. That code never, again, no platform ever affects any other platform. Any change you make in any platform, in any platform you make will not affect the others. The code is never loaded in. Because of the structure of the inclusion, where at the end of the baseline quat.h, your entry, kind of your API, your entryway into your quaternions, at the end, it only includes the one for your platform that you defined in your build system with that one macro, PLT SIMD. So again, in ARM, I will never load an SSE file in. So I can do whatever SSE stuff over there I want, however exotic. I don't have to wrap it in an if-def. I don't have to try and hide it anywhere, because it will never be seen in a context for which it's not valid. The only interaction is up the derivation chain. So if I make a change to SSE2, some detail in there when I do that will affect SSE3, that will affect AVX, potentially, right? If there is some interaction to be had. they do see it because AVX is dependent upon SSE4, is dependent upon SSE3. But any change to SSE3 has absolutely no effect on SSE2, original SSE, the common implementation, or any other, again, Neon, whatever. Nobody else will ever see that. It is totally isolated. And when doing cross-platform development, that is a huge thing. The fact that I can be secure in knowing I can make these changes, I can even mess up whatever I want to mess up, and all of this is safe. And one of the projects that I worked on was on an embedded device. And it's a company that's been putting out devices for 20 years. So they have a whole range of devices. And it's really easy to go in and make a change for the device you're working on, and all of a sudden, I mean, I've done a number of contracts for this one company. Well, on one I went in there, it was a new group I'd never dealt with before. My very first commit, I broke 2 of 8 builds. And even more so, it was easy to do, especially because I didn't even know they existed. As it turns out, I didn't even have access to those. But I broke them, and I was told, well, you have to test on that. And I said, well, thank you, give me access. But if it was isolated in this way, I couldn't possibly have broken it. I was writing code for one specific device, and had it been segmented out, had it had an inclusion mechanism like that, I could have never possibly broke it. I wouldn't have had to stress about it. I wouldn't have had to walk around the company being, oh, hey, yeah, you're that contractor who broke the build. So that's where the real power is. But certainly if there was some kind of cross-platform library, I've done a lot of work in video games. If there's a game engine, open source or something, if they wanted to talk about it, I would definitely look into that. I've been tempted to see if I can take the Unreal Engine, rip out their vectors and quaternions, put this in, and then just put a little facade layer over and see if it'll speed it up. Now, part of that too is that I get a build for my specific machine, using the source. It's not, if I go and try and run it on a different generation of Mac, it might not work. But the question is even with a facade layer in place, will it still be more highly optimized? My guess is yes, but as everybody says, measure, measure, measure. Guessing is easy, getting it right is tougher.
Okay, thank you.
You're welcome.
Hi, this is a great strategy for doing the platform independence, but how would you apply this to a situation in which a common your common library is not even possible? So it applies in that case. You still have separation. What you don't have is you don't start from a root. You don't have this one single tree of SSE. Here's the SSE branch of the family. Here's the Neon branch of the family. You have no common. You'll still have. Well, no, you still have a common. You'll still start from a common tag because that's what's going to unify everything, but you won't have a common implementation. And so the one difference here is, okay, great, I wrote this stuff that might be based off of Windows OS, and this stuff's running great. Now I switch to the Mac. No, I'm dead in the water. I need to implement all those things on the Mac. I can't rely on the common implementation. The tag is there to unify my ability to look at it, but if there is no common implementation, yes, I just can't run without first implementing. I can't rely on that. But what I still get though is here's my Windows branch, here's my Mac branch. When I have the next version of the Mac operating system, there's new features or something like that, I still get the revision benefit of when I go to do revision 2 on the Mac, I can be sure that everything I've done before that works to revision 1 still works when I go to build just for that. All right, thank you.
Yep. Okay.